Welcome to lecture number 24 for ECE 476 Advanced Embedded Systems. In this lecture, we're looking at measuring acceleration and light using a Raspberry Pi Pico and Python. So the Pi Pico has got 4 analog inputs, each is 12 bits. Those are connected to the I/O pins right here. With the analog inputs, you can directly read sensors whose output is voltage, and you can read sensors with the output of current or resistance, along with, if you include some circuitry. In this lecture, we're going to look at measuring acceleration and light. With these, we can build a magic 8-ball, measure your vertical leap, and build a solar tracker, basically an electronic sunflower. So let's start out with acceleration. There's analog and digital sensors. We'll start with an analog sensor. The ADXL335 is an analog accelerometer you can get from Amazon. It operates at 3.3 volts, anything between 3 and 5 volts works, operates over a range of plus minus 30 G, and has 3 analog outputs, acceleration in X, Y, and Z. Now 0G reads as 0.7 volts, and the sensitivity is 0.15 volts per G, so I can scale that. Once you get a voltage out, the offset's 0.7 volts, 0.7 means 0, and the gain should be multiplied by scalar. That scalar's 3.3 over 65,000 gives you volts. 9.8 G is 0.15 volts based upon the sensitivity. Multiply it all out, it's 215.6. So here I've got the acceleration. Okay, to illustrate using the ADXL335 accelerometer, I'm using a slightly different board. This is the Pi Pico development board without the graphical interface, doesn't have the joystick. Basically, I want access to all 3 acceleration pins. So if I just take the raw reading X, Y, Z, this is X, Y, Z. Z is out of the page. As I tilt the board, you can see X is changing. The other way, this is Y changing. And Z is also changing. That's just the raw readings from the analog input. If I make the scalar 1 for now and display AX, AY, AZ, so I'm just reading these numbers. This is what I'm returning and displaying them. I'm going to just do an offset, and what I should see is in the X direction and Y, acceleration is 0. So I tilt the board, their X is changing, plus minus, Y changing, plus minus, and Z. Throw in the scalar to convert it to meters per second squared. Here's your acceleration X, Y, and Z. X and Y are 0, that's 9.8-ish. Upside down gives you minus 9.8. The X direction goes minus 9.8 plus 9.8. Y direction. Okay, so there's your acceleration, X, Y, Z. So going back to the board that we're using in this class, I've got the X, the analog inputs. The potentiometer is affecting the acceleration in the X direction and Y direction. The Z direction is really the only one I have. As I turn the board around, turn the correct board around, see the change in the acceleration in Z. Okay, that's one way to measure acceleration. A second way is a GY521 digital accelerometer. This sensor is capable of 3 to 5 volt operation, meaning it works with a Pi Pico. It will work anywhere between plus minus 2 Gs up to plus minus 16 Gs. And will also measure rotational acceleration or rotational velocity from 250 to 2000 degrees per second rotations. Also supports both I2C and SPI communication. Now, to drive this sensor, you need to come up with the driver circuits. If you go to Pepi 80, This is actually a really nice website where whoever the author is has come up with tons of different articles for using the Raspberry Pi Picos. So it's got using NeoPixels, sensors, so on. If you search under accelerometer, it'll pull up instructions for using a GeeekPi accelerometer, along with the driver codes. So to get the digital accelerometer to work, you need both hardware and software. In terms of hardware, the drivers from Pepe 80 use the I2C interface. It's to connect the GY521 to power, ground, and GP0 and 1 using SPI or I2C communication. In terms of software, you need two routines, imu.py, or Python, and vector3d.python. So what you need is, stop this puppy. You need to get those and download them, imu.py to your Pi Pico, and vector3d.py goes to your Pi Pico. Get those on your Pi Pico. Then the calling routine looks like the following. I need to import the 6050 from IMU. That's one of the libraries you would download. Turn on the I2C port, or I2C port 0, indexing on pin 0 and 1 at 400 kilohertz. Then read the gyro XYZ, read the acceleration X, Y, and Z. Scaled, it gives it in G's, point to convert to meters per second squared, times 9.8. Shifted, to get the DC term right. Also measures the accelerometer, or the rotational velocities, and then display them. So that's pretty much all you need to do to read it. If I run this, here is the acceleration XYZ, again 9.8. If I flip, a bad wire connection there. There's acceleration XYZ. As I rotate the board, see acceleration Z is changing, X and Y are changing. That's another way to read acceleration. And the reading time is 1.96 milliseconds to read the acceleration, 1.9 milliseconds to read the rotational velocities, and the corresponding code. So, with that, let's have some fun. Let's come up with a program for Magic 8-Ball. So Magic 8-Ball is a device. You ask it a question, you talk to the Magic 8, shake the ball, then flip over to see what the answer is. Let's do that with an accelerometer. And I'm only going to use the Z-axis because the board that I'm using has two of the analog inputs already taken up, and using the analog accelerometer. So let's go to the Python code. What the Magic 8-Ball does is when I start out, again, these are all the different fortunes, your random fortune between 0 and 19. I'm going to ask it a question. It checks the Z-axis and makes sure that Z is positive. Got the Magic 8-Ball talking to the Magic 8. Ask a question 3 times. Then for 3 times, check to see if the acceleration in the Z direction goes bigger than 5, less than -5. Repeat 3 times. Tells you to turn over the Magic 8-Ball, basically flip the sensor to find your answer. Then picks a random reading. So let's try that. I'll ask it, will the Vikings win the Super Bowl this year? Shake, shake, shake. Flip it over. Oh, curses. Okay. Will the Vikings win their home opener? Shake, shake, shake. Shake, 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 shake. Flip it over. No, okay, not a good year with the Vikings. So that's your magic 8-ball. You can now answer all of life's questions using your Pi Pico board. All right, now that we have acceleration, we can do some other fun things. Let's measure how high I can jump using the Pi Pico board. Now, the idea here is that when you jump, when you're on the ground, the acceleration due to gravity is 9.8 meters per second squared. When you're in free fall, acceleration should drop to 0. So by measuring how long I'm at 0 g's, I know how long I'm in the air. If I know how long I'm in the air, I can calculate distance from 1/2 at squared. But you got to remember that t is actually half that time. The 1/2 at squared is the time from the apogee to ground. The total time is twice that. So take the t that I measure, that's t, the time at 0 g's, divide by 2, plug it in, that's my distance for my vertical leap. Okay, let's see if that works. I'm going to start out the free fall test. I'm going to take the accelerometer and just drop it onto a pillow. Start out with the accelerometer 1 meter above the ground, measured with a ruler. Drop it. Measure the acceleration for 2 seconds. Sampling every 5 milliseconds, and store the data in a file and see what it looks like. What I should see is the acceleration is 0 while falling, and it should fall for 1 meter. So doing that, taking it, dropping it onto a board, dropping it onto a pillow from 1 meter, here's the acceleration versus time. So here's the acceleration versus time for a dropping of 1 meter. The acceleration is normally 9.8 meters per second squared. That's at rest. I drop it. Acceleration goes to 0-ish. Hits the pillow, bounces, then comes back to rest. So it looks pretty good. The time that I'm at free fall, time at 0 acceleration, is right here. That reads as 0.784 meters, so it's a little bit off. 1 meter would actually be this distance. So, sort of. Now that I am kind of confident that works, more or less, I can repeat with the sensor at my waist. What I'm going to do is crouch down, hit the button 15, wait for beep, jump as high as I can. When I land, the beep's starting the data, jump as high as I can. I'll then land. It will collect 2 seconds worth of data, sampling every 5 milliseconds. So observation is at about a 14 centimeter jump. That's kind of a guesstimate. Again, not real impressive, but hey, I'm getting kind of old. The acceleration that I measured was this. This is when I'm crouching down. There's my jump, land, coming back to rest. So when I'm in the air, I was actually holding this in my hand rather than my waist, so my hands are moving up and down, probably causing some of this bouncing motion. It'd be better if I tied it to my waist. If I measure the time when the acceleration is less than 1 meter per second squared, this time right here, the time winds up being the difference between 1.08 seconds and 0.735 seconds. Doing 1/2 at squared, where t is divided by 2 then. That's the duration of the jump, and the height then is 14 centimeters, which seems about right. Okay, so let's try that. Crouch down, hit the button to start the recording. Jump. And there's the recorded acceleration in the z direction. So when I do that, that also creates a file. I can take that file, open it, find the time that I'm below 1, or with some coding, I could actually do that automatically. Find the time where the acceleration is less than 1 meter per second squared. calculate the time, the distance, and find out how high you can jump. So some things you can do with accelerometers. All right, new topic. Let's measure light, and with that, build a solar tracker. So there's a couple ways to measure light. One is a light CDS light sensor. This is a photoresistive sensor. Basically, the semiconductor, cadmium sulfide, is an insulator at 0 degrees Kelvin. If you hit it with photons, the photons kick electrons out of the covalent bond. More charge carriers gives you less resistance. So as light level goes up, the resistance goes down. So by measuring resistance, I've got a measurement of light. Now the relationship in general for a light sensor is A times lux to the minus B power. A and B are constants, varies with each sensor. If you pull up the data sheets for like the PDV P8001 sensor, it tells you that at 10 lux, the resistance is between 3K and 11K. It's a lot of variation. At the sensitivity, the log of the resistance at 100 lux minus 10 lux over the log of 100 lux minus log of 10 lux is 0.6. That's this term right here. So with that, I can come up with a mathematical relationship. 7,000 ohms is A at 10 lux to the minus 0.6. Solve for A. So that's roughly the relationship between resistance and lux. If I plot it, here's what it looks like. It's linear on log-log paper. As light level goes up, R goes down. Problem with resistance is that's hard to measure. If I use a voltage divider, in this case I can choose a 7K resistor, like mid-band resistance, convert resistance to voltage. So here's your light sensor, here's a 7K resistor, and 3.3 volts. The resulting voltage versus lux looks like so. So by measuring voltage, I can tell you light level. This is going to work best over this range, between like 1 and 100 lux. If I want to have a lower light level, I want to use a larger resistance. A higher light level is a smaller resistance. You kind of want to tune it so that the resistor use up here is the nominal light level. But anyway, that lets me measure light. That's one way to do it. A second way is to use a photovoltaic sensor. This is basically a light sensor, solar cell. What solar cells do is they convert sunlight to electricity. The power is proportional to solar intensity. And to give an idea, well, times efficiency. To give an idea of the efficiency of solar cells are right around 13 to 23% efficient at converting sunlight to electricity. That's actually pretty good. Most plants are between 0.2 and 2% efficient for photosynthesis. Crops are between 1 and 2% efficient. The world champion for photosynthesis is sugarcane. That's a whopping 8% efficient. It's part of the reason that Brazil uses sugarcane for petro. You can grow sugarcane in Brazil. In theory, the best you could ever do is 11% efficient. Nature hasn't gotten there yet. With solar cells, we could actually do better than nature. Solar cells are between 13 and 23% efficient for commercial brands. Some research-grade PVs are up to 39% efficient. So they're actually not too bad. With solar cells, I can measure how bright the sun is. So, for example, you can go outside, measure the intensity at dawn, noon, evening. To do that, I want to convert, add a resistor across the solar cell so that the voltage is power. This will give me the power out, V squared over R. So based upon the voltage, I know the power, V squared over R, is outputting 92 milliwatts, 191 milliwatts, 161 milliwatts. Noon is when to be the hottest, the brightest. So I can see that at dawn and evening, the sun is getting less bright. This is going through more atmosphere. But throw in a constant, I can tell you the solar intensity. The solar intensity should be 1370 watts per square meter. That's nominal sunlight. That's probably in the desert, 0% humidity at noon. It'll be less than that in Fargo. So some fun with light sensors. Well, once I have a light sensor, what I can do is build a solar tracker. Previously, we had a servo motor that can sit there and rotate on the left and right, tilt up and down. Put a solar cell on top of this, and I can sit there and see what is the sun intensity based upon angle. What I want to do is turn it so the intensity is the brightest, or the voltage is the highest. What that does is that gets it pointing at the sun. As the sun moves, I want to constantly adjust where the solar tracker is pointing. If you do that, you've built an electronic sunflower, or scale it up with solar cells. I have a solar cell that's tracking the sun. What that does for you is you have a more efficient solar cell. It's always pointing into the sun, always getting maximum power out of my solar cells. But we'll leave that as a homework assignment. Some way to do a search. I want to find out what tilt gives me maximum voltage, what azimuth gives me max voltage. Put the two together, I should be able to point at the sun and follow it. So kind of in summary, with acceleration and light sensors, you can have both analog and digital sensors. Acceleration especially is available for analog and digital. That lets you detect orientation, shaking, stuff like that. With that, you can build a magic 8-ball, measure how high you can jump, stuff like that. Light sensors detect light, of course, and you have both resistive and voltage outputs. With a light sensor, you can detect room conditions, like is the room light or dark. You can count how many times the refrigerator door is opened. You can do things like track the sun. Both are pretty easy to interface with the Pi Pico. And that's lecture number 24 for ECE 476.